Okay, so this is the 2019 VCAA Chemistry exam. We're up to question 6 now. We're back on board. So let's have a look at what we've got. We've got some energy content and some information about a type of food here. It's bread by the looks of it. Now, calculate the energy in kilojoules provided by the protein and fats and oils in 100 grams of this wholemeal bread. So I've got the protein here and I've got the fats and oils. Now, energy content of food is in our data booklet here. So if I take my page 2, which page am I at? I'm up to page 10, and I can see the fact I've got energy content for various foods. So therefore, my protein is going to be 17 kilojoules per gram, and my fats and oils is 37 kilojoules per gram. I've got per 100 grams, I've got this much, so therefore the energy from my protein is going to be 9.1 times 17. My energy for my fats and oils is going to be 2.5 times 37. Let's get my trusty calculator up here, and I go 9.1 times 17. That's going to be 154.7, and 2.5 times 37. That gives me 92.5. Total those two up. That plus 154.7 is going to give me 247.2 kilojoules. Now I can see I've got two sig figs here, so I'm going to report that as being 250 kilojoules, or 2.5 times 10 to the power of 2 kilojoules, just to make sure my sig figs marry up there, which is fantastic. That's first question done. Next question is, name a model used to explain the mechanism by which an enzyme breaks down proteins. Now the model or the mechanism is either going to be lock and key mechanism, or we also have a thing called the induced fit model. The lock and key says our enzyme's rigid, which is kind of like an old school model, whereas the induced fit says it can actually bend a little bit because bonds are slightly flexible and it's more like a glove. Now, the idea here is it's only 1 mark, it's going to be one or the other. We just need to name one. So therefore, that's going to be my answer there. That or that would be reasonable. Part C. Proteins can be denatured as an increase in temperature. Describe what happens to the bonding in the protein structure when it is denatured by an increase in temperature. Alrighty, so we need to talk about denaturation in protein structure. So first things here is denaturation. Denaturation is the loss of the secondary and tertiary and quaternary structures of proteins. Alrighty, now this is to do with the breaking of intermolecular forces holding these structures together. Now this is only a 1 mark question, so I think that should be enough to answer our 1 mark. But what I could do is, if I had to elaborate on this a bit more, I'd say the secondary structure is to do with hydrogen bonds between amide groups. I'll then talk about the tertiary or quaternary structure is to do with intermolecular forces between side chains. And that just then also explains the fact that what's happening here is, as I increase the temperature, I'm breaking these bonds which hold the structures together, and the secondary structure is between hydrogen bonds between different amide groups on our molecule, whereas our tertiary and quaternary is all about the interactions between side chains. So hopefully that's going to give me my mark there anyway. Probably more information than I need for 1 mark, but definitely explains the bonding and protein structure when things are denatured. Bonding is covered by intermolecular forces, hydrogen bonding, and these guys here. And the protein structure is covered by talking about both the secondary, tertiary, and quaternary structures. Now, question D. Carbohydrates can be present in the body in many forms. Name the polysaccharide that is used to store energy in the body. Let's have a look at what this is. Now, polysaccharides, that comes in like starch, amylopectin, and stuff like that. But the one used to store starch in or store energy in the body is called glycogen. Glycogen. Alrighty, this is a polysaccharide made from alpha glucoses all bonded together and highly branched, which means it can then break down really quickly and give us glucose when we need it. The next question here is explain the difference between the glycemic index of amylose and amylopectin. What do I need to know about these two things here? First things first, I need to know which one is higher. Now, amylopectin is higher. So I'm going to say amylopectin has a higher GI than amylose. Now, then I'm going to talk about the reason why that is. I'm going to say then amylopectin is much more branched than amylose. This is something you should know, but also in our data booklet, let's grab this out here. My data booklet here, going into the structure of these two things. Can't really see it really well. Actually, there it is. Amylopectin's got a branch coming off, whereas amylose is straight chain. So therefore, amylopectin is much more branched than amylose, which provides better access for enzymes and water to the ether linkages. Alrighty, so therefore you're going to have better access from our enzymes and water to the ether linkages. This means, so therefore, glucose is released faster, because therefore I need to explain why or what glycemic index is all about. And let's go through this again. The glycemic index is all about how fast glucose is released to the bloodstream. Amylopectin has a higher GI than amylose because it is much more highly branched. Therefore, it provides better access for enzymes and water to the ether linkages to allow for that hydrolysis to happen. And that should give me my 2 marks. Probably, I reckon that's worth 3 marks personally, but anyway, let's move on. Canola oil is one of the usual ingredients in bread. Canola oil is an omega-3 fatty acid. Why are the fatty acids classed as omega-3? Alrighty, this reason for the omega-3 is because the carbon-to-carbon double bond is on the 3rd carbon from the omega non-carboxyl end of the fatty acid. And that's by definition what it's all about. It's to do with a carbon-to-carbon double bond, and it's on the 3rd carbon from the omega, the other end. So for example, if I have an example here, I can do an example. I've got lots of room here. I can talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever it is. And I can say 1 carbon, 2 carbon, 3 carbons. It is here. Here. Just to also explain what I mean by this. The fact that it's on the 1, 2, 3, this is where the carbon here, that makes it an omega-3 fatty acid because that's where our double bond actually is. Now let's go into our next question. Part F. This has got lots of parts, this question. The wholemeal bread undergoes complete combustion in a bomb calorimeter containing 200 grams of water. Assume that all energy of the combustion is transferred to the water, which it never actually is, but we'll move on. Calculate the mass of bread needed to raise the temperature by 6 degrees Celsius. So I've got 200 grams of water. I know that energy, or sorry, I should say Q equals MC delta T. So therefore my mass is 200, my C is 1.48, and my temperature change is 6 degrees. That means my energy is 200 times 4.18 times 6 gives me 5,006 joules of energy. Now, what do I know about my bread? Let's go back here. I know that 100 grams gives me 1,000 kilojoules. What that means is that 1 gram equals 10 kilojoules. So therefore, 1 gram equals 10,000 joules. So what I can do then is say I've got 5016. If I divide that by what 1 gram is, which is 10,000, I'll end up with, divide by 10,000, 0.5016 grams of bread. Now I did a calculation, so let's check my significant figures. I've got 6 degrees. That's one significant figure, so it's going to be 0.5 grams of bread for that particular answer, including significant figures, because this guy here is only one significant figure. We can only go to the least number of significant figures in our response. So that's how much bread I actually require. Let's have a look at the next part. The combustion of bread was investigated using a different method. The bread was ignited under a beaker containing 200 grams of water, which was set on a tripod. The equipment is shown below, and we've got this one here. Now, in this case, 1.2 grams of bread was needed to raise the temperature by 6 degrees instead of my 0.5 grams. Calculate the energy efficiency of the energy transfer in this combustion. Alrighty, so what energy efficiency is basically about how much energy is, I guess, used. But I can do this in a simple way by saying this is 100% efficient. So therefore, what is this? Let's go with 0.5 divided by 1.2 times 100 equals, divided by 1.2 equals 41.8%. And that should be my answer for that one. And let's have a look at this. Again, I'm using just 6 degrees Celsius, so therefore it should be just one significant figure, so therefore it's going to be 40%, or 4 times 10 to the power of 1% efficient. And that is my response to the last part of question F about efficiency of my system here. And that is all of question 6 done. Hopefully that's going to give me 10 marks. We can always check the examiner's comments if we need to make sure these are right.